In this lecture video, we start looking at inference procedures for single populations. In particular, we're going to be looking at techniques for making inferences about a single population mean, a single population variance, and a single population proportion. Now let's first start talking about inferences about a single population mean. We'll be looking at hypothesis tests about the mean of a single population. We'll be looking at how to estimate the mean of a single population via point estimation and also via confidence interval estimation. We'll look at how to construct lower and upper confidence limits. And we'll also look at sample size problems, how to determine the sample size required for hypothesis tests to have a certain amount of power and for confidence intervals to have a certain level of precision. So the first thing we need to do in developing a test is to look at the sampling framework. Here we're going to be looking at the situation where we know the population standard deviation. So let x1, x2, and so forth up to x sub n be a random sample of size n from a normal distribution with mean mu and variance sigma squared. Let x bar, s squared, and s denote the mean, variance, and standard deviation, respectively, of this sample. Now recall that the standardized random variable z equal to the difference between x bar and the true population mean divided by the standard error of x bar. And in particular, remember that the mean of the sampling distribution of x bar is the mean of the population we're sampling from, mu. And so what we're doing here is we are subtracting off the mean of the sampling distribution of x bar and then dividing that difference by its standard error. And in particular, this is the standard error of x bar. So recall that if we're sampling from a normal distribution and we standardize x bar, then the standardized version of x bar has a standard normal distribution. Now, this can be used as a basis for developing hypothesis tests and procedures for constructing confidence intervals for mu when the population standard deviation sigma is known. So let's consider testing the null hypothesis that the population mean is equal to some hypothesized value, mu sub 0, or mu naught, versus the alternative that the population mean is not equal to that hypothesized value. And let's do that at a significance level of alpha. Now, questions that we need to consider in order to determine a rejection criteria for this test is to consider these questions. How does x bar behave under the null hypothesis? How does x bar behave under the alternative hypothesis? And how can the differences in behavior of x bar under the null and alternative hypotheses be used to come up with a way of discriminating between the null and alternative hypothesis? In other words, identifying which of those two hypotheses we believe to be the true state of affairs based on the data, and in particular based on the observed value of x bar. Now, if the null hypothesis is true, in other words, if the mean of the population that we're sampling from is equal to the hypothesized value of mu sub 0, then the sampling distribution of x bar will be centered right at mu sub 0. Mu sub 0, in that case, will be the mean of the sampling distribution of x bar. On the other hand, if the alternative is true, then the sampling distribution of x bar will be centered at some other location. Now, the farther mu is from the hypothesized value mu naught, the farther x bar will tend to be from mu naught than it would be if the null hypothesis were in fact true. So intuitively then, values of x bar that are far away from mu sub 0 will be evidence against the null hypothesis. Now, note that if the null hypothesis is true, then the probability that x bar is between this lower endpoint and this upper endpoint will be equal to 1 minus alpha. And if you think back to the previous lecture video, where we wrapped up the general principles of statistical inference, we looked at a probability like this. This was one of the examples that we looked at the end of that section. So we're quantifying the likelihood that x bar takes on a value between these two endpoints, and that probability is 1 minus alpha. And by the complement rule, the probability that x bar takes on a value outside of that interval, either less than the lower endpoint or greater than the upper endpoint, will therefore be alpha. And so for a fixed value of the hypothesized value, mu sub 0, we have what we would call the acceptance region for the test. This is the set of values of x bar that are consistent with the null hypothesis and lead to its acceptance at a significance level of alpha. And so this acceptance region is this interval that ranges from this lower endpoint, mu sub 0, the hypothesized value, minus z sub alpha over 2 times the standard error of x bar, up to the upper endpoint, mu sub 0, plus z sub alpha over 2 times sigma over the square root of the sample size, which again, this is the standard error of x bar. So this interval is called the acceptance region, and it's the set of values of x bar that would lead us to accept, or we might say not fail to reject the null hypothesis. The complement of this interval, of the set of values that are outside of this interval, so the union of these two intervals from minus infinity up to, but not including the lower endpoint here, so mu sub 0 minus z sub alpha over 2 times the standard error of x bar, union with the interval with lower endpoint mu sub 0 plus z sub alpha over 2 times the standard error of x bar up to, but not including obviously positive infinity. This is the rejection region. This is the set of values for this particular form of a test that would lead us to reject the null hypothesis. These values, these two intervals, the union of these two intervals, comprise the set of values of x bar that are inconsistent with the null hypothesis and therefore lead to its rejection. Remember that the probability that if the null hypothesis is true, the probability of observing a value of x bar in this set is only alpha. Now we can, instead of stating an acceptance region and rejection region, we can formulate our decision rules this way. We could say that we are going to accept, or in other words, fail to reject the null hypothesis if x bar takes on a value between this lower endpoint and this upper endpoint, which is equivalent, by the way, you'll notice, to saying that we are going to accept the null hypothesis if the hypothesized value of mu naught, is between these two endpoints. So x bar minus z sub alpha over 2 times the standard error of x bar, and x bar plus z sub alpha over 2 times the standard error of x bar. And similarly, we would reject the null hypothesis, in other words, conclude that the null hypothesis is false, and therefore that the alternative is true if we observe a value of x bar either less than mu sub 0 minus z sub alpha over 2 times the standard error of x bar, or if we observe a value of x bar greater than mu sub 0 plus z sub alpha over 2 times the standard error of x bar. Now, this can be reformulated or restated in terms of mu naught. So we would reject the null hypothesis if the hypothesized value of mu naught is less than x bar minus z sub alpha over 2 times the standard error of x bar, or if the hypothesized value of x bar is greater than x bar plus z sub alpha over 2 times the standard error of x bar. So we can state the acceptance and rejection criteria either in terms of sets like these, so we would have an acceptance region and a rejection region, or we can, again, restate it in terms of actions or decision rules that involve these actions. And we can also think about things this way. So for a fixed value of x bar, we can think of plausible and implausible regions. So the plausible region, based on, and then notice that I'm getting this formulation from the second set of bullet points in the previous slide. And so the plausible region, or what I'm calling a plausible region, would be the interval with lower endpoint x bar minus z sub alpha over 2 times the standard error of x bar, and upper endpoint x bar plus z sub alpha over 2 times the standard error of x bar. Now, this is the set of plausible values for mu in the sense that the null hypothesis would not be rejected in favor of the alternative for any value of mu naught, the hypothesized value in this interval, based on the observed value of x bar. And so we can think of the lower endpoint of this interval as being the smallest value of mu sub 0 for which the null hypothesis would not be rejected. And we can think of the upper endpoint of that interval as being the largest value of mu naught for which the null hypothesis would not be rejected. The implausible region would be given by this union of intervals. All right, so I'm not going to read that off, but you can see that there. And so based on the observed value of x bar, the null hypothesis will be rejected in favor of the alternative for any value of mu naught in this set. Okay, so we've got plausible region and implausible regions. The plausible region is the set of values of mu naught, the hypothesized value, for which we would not reject the null hypothesis. And the implausible region is a set of hypothesized values for which we would reject the null hypothesis. All right, now let's look at a different test. So suppose we're interested in testing the null hypothesis that the population mean is greater than or equal to a hypothesized value or specified value of mu sub 0 against the alternative that mu is less than that value. And we want to do so at a significance level of alpha. So again, we need to ask ourselves the questions: how does x bar behave under the conditions of the null hypothesis? How does x bar behave under the conditions of the alternative hypothesis? And can we use the difference in behavior of x bar under the null and alternative hypotheses to come up with a way of discriminating between the two hypotheses? And so if the alternative is true, in other words, if mu is, if the true value of the population mean is less than the hypothesized value, then the sampling distribution of x bar will be centered to the left of where it would be were the null hypothesis true, right? If the null hypothesis is true, remember that the sampling distribution of x bar is going to be centered right at mu, wherever mu happens to be. And so if mu is greater than this value of mu sub 0, greater than or equal to mu sub 0, then the sampling distribution of x bar will tend to be, will be centered either at mu sub 0 or to the right of that point. On the other hand, if the alternative is true, then x bar will be centered somewhere to the left of mu sub 0. As a result, if the alternative hypothesis is true, then x bar will tend to take smaller values under this alternative hypothesis than it would take under the null, because those that would be the intervals over which we would have maximum probability. And so intuitively then, small values of x bar will be evidence against the null hypothesis. Now, note that if the null hypothesis is true, then the probability that x bar is greater than or equal to mu sub 0 minus z sub alpha times the standard error of x bar, this probability is at least 1 minus alpha. And so therefore, by the complement rule, the probability that x bar is less than that point is less than or equal to alpha. And so based on these probabilities, the values of x bar greater than or equal to mu sub 0 minus z sub alpha times the standard error of x bar are consistent with the null hypothesis, while values of x bar less than that point, mu sub 0 minus z sub alpha times the standard error of x bar, are inconsistent with the null hypothesis. And remember, what we're looking for in order to come up with a rejection region is to find the values of the test statistic that are inconsistent with the null hypothesis. And so, therefore, for a fixed value of mu sub 0, the hypothesized value of mu in this setup, in this test, then the acceptance region, in other words, the set of values of x bar that are consistent with the null hypothesis and therefore would lead to its acceptance at a significance level of alpha, are given by the values in this interval. And the rejection region, the set of x bar values that are inconsistent with the null hypothesis and would therefore lead to its rejection, again at a significance level of alpha, are given by the values in this interval. Now, again, we can restate this in terms of decision rules. And so for this situation, based on these intervals that we've identified here, then we would accept the null hypothesis if x bar is greater than or equal to mu sub 0 minus z sub alpha times the standard error of x bar, and we would reject the null hypothesis if x bar was less than that point. Now, again, we can reformulate or restate these acceptance and rejection rules in terms of the hypothesized value mu sub 0. All right, and so we stated in a slightly different way. We would say that we would accept the null hypothesis if the hypothesized value, mu sub 0, is less than or equal to x bar plus z sub alpha times the standard error of x bar. And we would reject the null hypothesis if the hypothesized value mu sub 0 is greater than x bar plus z sub alpha times the standard error of x bar. And so thinking about the decision rules in those two ways, then we can speak of plausible and implausible regions. The plausible region is the set of values of mu, and this is in the sense that the null hypothesis, mu being greater than or equal to mu sub 0, would not be rejected in favor of the alternative, that mu is less than mu sub 0, for any value of the hypothesized value, mu sub 0, in this interval that we're calling the plausible region. And this, obviously, this region is based on the observed value of x bar. The implausible region is given by this interval, and so based on the observed value of x bar, the null hypothesis would be rejected in favor of the alternative for any value of mu in this set, this implausible region. And finally, let's consider testing the null hypothesis that the mean is less than or equal to some pre-specified value, mu sub 0, against the alternative that mu is greater than that value. And again, we will do this at a significance level of alpha. And so again, we ask ourselves the questions, how does the sample mean x bar behave under the null hypothesis? How does x bar behave under the alternative hypothesis? And can we use the differences in behavior of x bar under the null and alternative hypotheses to come up with a way of distinguishing between the two situations. And so if the alternative hypothesis is true, then the sampling distribution of x bar will be centered to the right of where it would be were the null hypothesis true. As a result, x bar will tend to be larger under the alternative hypothesis than it would be under the null hypothesis. Intuitively then, large values of x bar will provide evidence against the null hypothesis. The question is, how large does X bar had to be in order for us to decide to reject the null hypothesis. Again, keeping in mind that we are performing this test at a significance level of alpha. Well, again, this is where we go back to what we know about the sampling distribution of X bar. We know that if the null hypothesis is true, then the probability that X bar takes on a value less than or equal to mu sub 0 plus z sub alpha times the standard error of X bar will be at least 1 minus alpha. And so by the complement rule, the probability that X bar takes on a value greater than this point, mu sub 0, and at the same point, mu sub 0 plus z sub alpha times the standard error of X bar, that probability would be less than or equal to 1 minus alpha. And so this is where we're going to get the rejection criteria for this test. In particular, so based on these probabilities, values of X bar less than mu sub 0 plus z sub alpha times the standard error of X bar, these values are consistent with the null hypothesis, and therefore they would not lead us to reject the null hypothesis. On the other hand, values of X bar greater than that point, those are the values of X bar that are inconsistent with the null hypothesis, and therefore would lead us to reject the null hypothesis. And so for a fixed value of mu sub 0, the acceptance region for the test is the set of values of X bar in this interval. This is the set of X bar values consistent with the null hypothesis at a significance level of alpha. And the rejection region would be given by this interval. This is the set of values of X bar that are inconsistent with the null hypothesis at a significance level of alpha. So stated in terms of decision rules, we would accept the null hypothesis if the value of X bar is less than or equal to this quantity, and we would reject the null hypothesis and conclude that the alternative is true if X bar exceeds that quantity. We can also restate these decision rules in terms of mu sub 0, the hypothesized value, in the ways listed here. And when we do that, that leads to, again, the consideration of thinking about this in terms of plausible and implausible regions, values. So, for example, the plausible region, for this case, for this particular hypothesis test, for a fixed value of the sample mean, the plausible region given here would be the set of plausible values of mu in the sense that the null hypothesis, which again in this case is that mu is less than or equal to mu sub 0, would not be rejected in favor of the alternative for any value of mu sub 0 in that interval based on the observed value of X bar. On the other hand, the implausible region given here, based on the observed value of X bar, the null hypothesis will be rejected in favor of the alternative for any value of the hypothesized value mu sub 0 in that set. And so to put all of these results together, we have three sets of hypotheses that we can test. We'll call these two-tailed test, and then we have two one-tailed tests. We have a left-tailed test and a right-tailed test. So the two-tailed test, again, is the null hypothesis that says that mu is equal to a specified value mu sub 0, with alternative that says that mu is not equal to that value. The left-tailed test has a null hypothesis that says that mu is greater than or equal to mu sub 0 against the alternative that says that mu is less than mu 0. And then the right-tailed test, the null hypothesis is that mu is less than or equal to mu sub 0 against the alternative that says that mu is greater than mu sub 0. So we've got these three kinds of tests that we can use, and the one that we would choose would depend on the research question, the problem that we are trying to answer. And as you know from your first methods class, that you always put what you're trying to prove, what you're trying to show, in the alternative hypothesis. Now, to keep track of these hypotheses and to link them with other aspects of the notes, for example, the rejection criteria and things like that, I'm going to label these hypotheses A, B, and C. So A will be the two-tailed test, B will be the left-tailed test, and C will correspond to the right-tailed test. And so the way that we have been formulating these tests thus far, the test statistic is X bar, the sample mean. And remember that in order to know how to come up with the rejection criteria, which we've already done, but I'm just summarizing this information, we have to know something about the sampling distribution of the test statistic. And so with a test statistic X bar, the sampling distribution of X bar, if the null hypothesis is true, then X bar will be normally distributed with a mean of mu sub 0 and a variance equal to sigma squared over n. If the alternative is true, then X bar will be normally distributed, the mean of which is mu, but it will be different than mu sub 0, and it will have the same variance in either case. Now, when I say here that the sampling distribution is normally distributed, remember that the underlying assumption here was that the population that we're sampling from is normally distributed. Now, if that's not the case, then what we will do is say that if the sample size is large enough, then we can appeal to the central limit theorem. And so in that case, for sufficiently large samples, the sampling distribution X bar will be approximately normally distributed. And so then all of these probability statements that we've been looking at up to this point, instead of being exact probabilities, they will be approximate probabilities. All right, and so then for the hypothesis A, the two-tailed test, the two-sided test, the rejection criteria, if we're using the sample mean as the test statistic, then we will reject the null hypothesis if X bar is less than mu sub 0 minus z sub alpha over 2 times the standard error of X bar, or if the observed value of X bar is greater than mu sub 0 plus z sub alpha over 2 times the standard error of X bar. For hypothesis test B, the left-tailed test, we're going to reject the null hypothesis if X bar is less than mu sub 0 minus z sub alpha times sigma over the square root of the sample size. And then for the right-tailed test, we're going to reject the null hypothesis if X bar is greater than mu sub 0 plus z sub alpha times the standard error of X bar. So these are the rejection criteria if we're using the sample mean X bar itself as the test statistic. Now, we can also use the standardized version of X bar as the test statistic, and that's typically what is done. And so to do that, we would, to calculate the standardized version of the test statistic X bar. So, and we'll notice that I'm going to denote the standardized version of the test statistic by zcalc. And so the way that we would calculate this is to subtract off. Let me just put it this way. We would standardize the sample mean, assuming that the null hypothesis is true. And so we would subtract from X bar the mean of the sampling distribution of X bar under the conditions of the null hypothesis. So subtracting off mu sub 0, and then dividing that difference by the standard error of X bar. And so with that standardized version of the test statistic, if the null hypothesis is true, then the standardized version of the test statistic, zcalc, will be standard normal. It'll have a standard normal distribution. And if the alternative is true, then zcalc will still have a normal distribution, or approximately so, if the underlying population itself is not normally distributed, but the sample size is large enough. So zcalc would still be normally distributed, or approximately so, but and it'll still have a standard deviation of 1, but it would have a different mean. And in particular, the mean would be equal to mu minus mu naught over the standard error of X bar. Using the standardized test statistic then, the rejection criteria become the following. For the two-tailed test, we would reject the null hypothesis if z-calc is less than negative z sub alpha over 2, or if z-calc is greater than positive z sub alpha over 2. For the left-tailed test, we would reject the null hypothesis if z-calc is less than z sub alpha. And finally, for the right-tailed test, we would reject the null hypothesis if z-calc is greater than z sub alpha. So let's look at an example. A company that packages salted peanuts in 8-ounce jars is interested in maintaining control over the amount of peanuts put into jars by one of its machines. Control is defined as averaging 8 ounces per jar and not consistently over or underfilling the jars. To monitor this control, a sample of 16 jars is taken from the line at random time intervals and their contents weighed. The mean weight of peanuts in these 16 jars will be used to test the hypothesis that the mean is indeed working properly. The machine is indeed working properly. If it is deemed not to be doing so, then the machine will be shut down and a costly adjustment will be needed. Now suppose that the mean weight of peanuts in 16 randomly selected jars is 7.89 ounces. Suppose also that it's known that from past experience that the standard deviation of the weight of peanuts dispensed by the machine is 0.2 ounces. The question is, based on this data, should the machine be shut down and adjusted or recalibrated? So the first thing we need to do is to define the notation that we'll use in setting up the hypotheses. And so I'll let U denote the mean weight of peanuts being dispensed by the machine. Then the null and alternative hypotheses are given below. The null hypothesis is that mu is equal to 8, and the alternative is that mu is not equal to 8. And so the null hypothesis is assuming that the machine is in control, and we're giving the data an opportunity to convince us otherwise. Notice that what we put in the alternative is what we're trying to show. In other words, that the machine is not in control. The mean weight of peanuts being dispensed is not equal to 8 ounces. Now we will use x bar as the tested, we'll use a significance level of alpha equal to 0.05 for the test. Now we can use either the sample mean or the standardized version of the sample mean as the test statistic. If we use x bar as the test statistic, then we will reject the null hypothesis if either x bar is less than 7.902 ounces or if x bar is greater than 8.09 ounces, 0.98 ounces. Now, as stated in the statement of the example, the mean weight, the mean of the sample was found to be 7.89 ounces. And since that it is less than the lower critical point of 7.902 ounces, the rejection criteria have been met, and so we would reject the null hypothesis and conclude that the alternative hypothesis is true. In other words, that mu is not equal to 8. And so to put this back into the language of the problem, we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the mean weight of peanuts being dispensed by the machine is not 8 ounces, and therefore the machine should be shut down and adjusted. Now, if we use the standardized test statistic, z-calc, then the rejection region will be to reject the null hypothesis, or the rejection criteria will be to reject the null hypothesis if z-calc is either less than negative 1.96 or if it's greater than positive 1.96. The value of the standardized test statistic, again, is obtained by subtracting the hypothesized value of the mean from the sample mean. So we subtract 8 from x bar, and we divide that by the standard error of x bar, which in this case would be 0.2, the population standard deviation, divided by the square root of the sample size. And so we get a standardized test statistic equal to negative 2.2. Now, since negative 2.2 is less than negative 1.96, the rejection criteria have been met, And so again, we would reject the null hypothesis and conclude that the mean is not equal to 8. Now note that while we will arrive at the same conclusion regardless of whether we use x-bar or z-calc as the test statistic, the standardized test statistic, z-calc, is what is typically used because the rejection criteria are more easily stated using the standardized version of the test statistic. Now the p-value is a measure of the consistency between the null hypothesis and the observed sample, in particular the test statistic computed from that sample. Smaller values indicate greater inconsistency between the test statistic and the null hypothesis. Another way to say that would be that smaller values indicate less consistency between the test statistic and the null hypothesis. Now, if the inconsistency between the null hypothesis and the test statistic is great enough, in other words, if the p-value is small enough, then we will be led to conclude that the null hypothesis is in fact false. Now, the p-value associated with an hypothesis test is defined to be the conditional probability of observing a value of the test statistic at least as extreme as that which has been observed for that sample under the assumption that the null hypothesis is true. And when we say at least as extreme, what we mean is as indicated by the alternative hypothesis, or in the direction of the alternative hypothesis. The p-value is therefore a function of the sample and depends on the hypotheses being tested. Now the p-value formulas for the three types of hypotheses that we're considering right now about the population mean, assuming that the population standard deviation is known, are given below. So for the two-tailed test, hypothesis test A, the p-value is equal to twice the probability that a standard normal random variable z is greater than or equal to the absolute value of the calculated value of the test statistic. For the left-tailed test, hypothesis test B, the p-value is the probability that a standard normal random variable is less than or equal to the observed value of z-calc. And if we're testing a right-tailed test, hypothesis test C, then the p-value is equal to the probability that the standard normal random variable is greater than or equal to the observed value of the test statistic. Now, I would just point out that of these three formulas, the only one in which we're calculating the absolute value of z-calc is in the first one, hypothesis test A, which is the two-tailed test. For both of the one-tailed tests, the left-tailed test and the right-tailed test, we do not calculate the absolute value of the test statistic. We take it as it is. So going back to the example that we just looked at, in the example above involving the company that packages salted peanuts in 8-ounce jars, what is the p-value of the test regarding the mean weighted peanuts they dispensed? Well, this is a two-tailed test, and so the p-value is equal to the 2 times the probability that the standard normal random variable is greater than or equal to the absolute value of the standardized version of the test statistic. Now, recall that z-calc is equal to negative 2.2, and so we have to take the square root, I'm sorry, not the square, but the absolute value of that. And so the p-value is twice the probability that the standard normal random variable is greater than or equal to positive 2.2. Now, looking this up from the standard normal table, we find that this probability is 0.01390. We multiply that by 2, and so the p-value is equal to 0.02780. Now, since the p-value, 0.02780, is less than or equal to 0.05, the significance level that we chose to use for that test, we would reject the null hypothesis at the 0.05 level of significance. Now, note that the conclusions will always be the same, regardless of whether we're using the p-value method, as we're using here, or the test statistic and rejection region method that we used when we originally looked at the example. In published results, the p-value method is almost always used. In fact, I can't think of a situation where I've seen the test statistic and critical point method ever used in a published research article, for example. The p-value method is almost universally used because it allows the reader of that research, the reader of the results, to draw their own conclusion based on the significance level, the alpha value that they choose to use. So, for example, the authors of a research article, in drawing their own conclusions, may have used a significance level of 0.05, but the reader of an article may have reason to use a different level of significance, for example, 0.03 or 0.01, or they may choose to use a larger significance level of 0.1. So for this reason, to give readers of research articles and consumers of these kind of articles or these results, to give them the opportunity to draw their own conclusions, the p-value method is typically used. Now let's look at an example here. It's a little bit more practice calculating p-values. So consider a test where the null hypothesis is that the mean of a population is less than or equal to 100 against the alternative hypothesis that the mean of the population is greater than 100. And we're told to assume here that the population standard deviation is equal to 5.0. A random sample of size n equal to 25 is selected from this population, and the sample mean, x bar, is calculated. Compute the p-value of the test and draw a conclusion based on a significance level of alpha equal to 0.05 for each of the situations below. So when x bar is equal to 98.5, when x bar is equal to 101.5, and when x bar is equal to 102.0. So what would be the p-value in each case, and what conclusion would we draw? Now, when x bar is equal to 98.5, the standardized version of the test statistic is equal to negative 1.5, and so from the standard normal table, the p-value of the test, which, by the way, this is a right-tailed test, and so the formula for the p-value is given by the probability that a standard normal random variable is greater than or equal to the observed value of the test statistic z tau. And so the p-value for this test is the probability that the standard normal random variable is greater than or equal to negative 1.5, and that p-value, that probability, is equal to 0.93319. And so because that is not less than 0.05, we would fail to reject the null hypothesis in this situation. In fact, I need to include that statement in my notes here, so let me do that, and I'll be right back. All right, so there's a statement. Since 0.93319 is not less than or equal to 0.05, we would fail to reject the null hypothesis at the 0.05 level of significance. Now, when the sample mean, or if the sample mean were 101.5, then the standardized version of the test statistic would be positive 1.5, and the p-value of the test would be 0.06681. Now, that's still not small enough. That's still not inconsistent enough with the null hypothesis in order to cause us to reject the null hypothesis, at least at the 0.05 level of significance, because, again, that p-value is not less than or equal to the chosen level of significance, which is 0.05. So again, in this situation, we would fail to reject the null hypothesis at the 0.05 level of significance. Now, if x bar were just a little bit bigger, equal to 102.0, then in that case, the test statistic is equal to 2.0. The p-value of the test is 0.02275, and because that is less than or equal to 0.05, we would reject the null hypothesis at the 0.05 level of significance. So you can see how we use the p-value method. In particular, we reject the null hypothesis and conclude that the alternative is true if the p-value of the test is less than or equal to the significance level that we've chosen to use for the test. Now, let's look at another example. Consider the test, again, and this is the same testing kind of situation, The null hypothesis is that the mean of a population is less than or equal to 100, against the alternative hypothesis that the mean is greater than 100. And again, we're told to assume that the standard deviation of the population is 5.0. Now, suppose that a random sample of size equal to 25 is selected from this population, and that the sample mean is found to be x bar equal to 102. Compute the p-value of the test, and then draw a conclusion based on each of the significance levels given below. So if we were to use alpha equal to 0.05, what would be our conclusion? If we were to use alpha equal to 0.01, what would be our conclusion? If we were to use any value of alpha that is greater than or equal to 0.02275, what would be the conclusion? And if we used a significance level, any significance level, strictly less than 0.02275, what would be the conclusion? Okay, so recall that in the previous example it was shown that when x bar is equal to 102, the p-value of the test is 0.02275. Now, if we were testing this hypothesis using a significance level of 0.05, then since the p-value, 0.02275, is less than or equal to 0.05, which is alpha, then we would reject the null hypothesis and conclude that the alternative is true. And we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the alternative hypothesis is true. Now, on the other hand, if we were to use a significance level of 0.01, then since the p-value is not less than or equal to 0.01, then we would fail to reject the null hypothesis. So while there's sufficient evidence at the 0.05 level of significance to reject the null hypothesis, there is insufficient evidence at the 0.01 level to do so. Now, note that when we fail to reject the null hypothesis, we are not claiming that the null hypothesis has been proven to be true. We are simply saying that it cannot be rejected at the 0.01 level of significance. Now, suppose that we use any value of any significance level that is greater than or equal to the observed value of the p-value, which was 0.02275. Well, in that case, since the p-value is or would be less than or equal to such a significance level, we would reject the null hypothesis and conclude that the alternative is true. And so using any significance level that is greater than or equal to the observed value of the p-value, there would be sufficient evidence to reject the null hypothesis and conclude that the alternative is true. On the other hand, if we use any significance level that is strictly less than the observed value of the p-value, then there would, because in that case, the p-value is not less than or equal to such a value of alpha, then we would fail to reject the null hypothesis. And so for any significance level alpha that is less than the observed p-value, there would be insufficient evidence to reject the null hypothesis. So these last two results in this in that previous example, 3 and 4, point out or help to show why the p-value is often defined or described as the smallest significance level for which the null hypothesis would be rejected for a given sample. So that is sometimes the way that a p-value is defined, and it's a useful way to think about it, that the p-value is the smallest alpha, the smallest significance level for which the null hypothesis would be rejected for a given sample. Now, because of this, the p-value is sometimes called the observed significance level. So you will see some textbooks and perhaps even some articles, instead of referring to the p-value, they may call it the observed significance level. And that, I suppose is fine, because calling it the observed significance level does, in a way, differentiate it from just the significance level, which is alpha. But the problem is that what you will see in many research articles, instead of calling the p-value, and instead of calling the p-value the observed significance level, they will drop the word observed and just call it the significance level. And that can be confusing because, again, the p-value is different than the significance level. The significance level is alpha. That is the threshold that we're using in making our decision. If the p-value is less than or equal to the significance level, then we reject the null hypothesis. And if it's not, then we fail to reject. So you just need to be aware of this usage of the term significance level, and you need to understand. You need to be able to understand in the context of where that term is being used, what the authors actually mean. But you do need to keep in your mind the difference, the distinction between the p-value of a test and the significance level that is being used as the decision criteria and threshold. So this is a good place to stop this lecture video. In the next lecture video, we're going to start talking about power and the probability of a type 2 error, characteristics of hypothesis tests. And so we'll pick that up in the next lecture video.